Hello everybody. Today we're going to talk about geometric sequences. So this is another type of number pattern. We talked the other day about arithmetic sequences, which are sort of like an adding pattern. And a geometric sequence is a multiplying pattern. Okay, so basically an example. I'm going to give you an example, give you a couple of examples actually, and then we'll pick it apart a little bit. Okay, so here's one. Let's say we have 3, 15, 75, and then let me think, 75 times, you can see what I'm multiplying by is 5. So 75 times 5 is 375. And then the next one, 1500, 75 times. Okay, so 1875. I'm trying to do this in my head, obviously. Okay, so, and this would keep going. Okay, so I'm multiplying in this case by 5. Another example of a multiplying pattern would be this one, 100, 50, 25, 12.5, 6.25. The next one would be 3.125. Okay, and so on and so forth. Here's another one, actually. I'm going to give you 3. Let's say I start at 5, and then my next number is -10, and then my next number is 20, and then my next number is -40, and then my next number would be 80, and then my next number would be -160. Okay, so you might actually be able to predict what's going on here. In each of these cases, in the first case, I picked a number to start with. In the first one, I picked the number 3. And then I picked a number to multiply by. So each subsequent term was 5 times the previous one. Right? So 15 is 5 times 3. 75 is 5 times 15. 375 is 5 times 75, etc. Okay? In the second sequence, I started with the number 100. And then this time, the number that I multiplied by was actually a number less than 1, right? I multiplied by a half. And that's fine too. That's also a type of geometric sequence. Doesn't necessarily need to get bigger. It can also get smaller. In the third one, I started with 5. And this time I actually multiplied by a negative value. I multiplied each term by -2. Right? So 5 times -2 is -10. -10 times -2 is +20. +20 times -2 is -40. -40 times -2 is +80. And that's why the terms keep flip-flopping between positive and negative. Okay, now the numbers, the number that you start with, the first number is called T1, which is the first term. And actually, I should mention this. It's often also called, and you'll see this on formula sheets, or you might see this referred to in other courses, also sometimes called A. And I don't think I mentioned this when I talked about arithmetic sequences, but in an arithmetic sequence, the first term is also sometimes called A. And then the number that you multiply by each time is called R. And R stands for the common ratio. And that's because it's the ratio that's common to consecutive numbers, right? So if I look at the ratio of 15 to 3, it's equal to 5 to 1. If I look at the ratio of 75 to 15, it's also equal to 5 to 1. If I look at the ratio of 375 to 75, also equal to 5 to 1. And you guys kind of get the idea, okay? So that's why that number is called R. And what we're going to do today, and actually what I should mention, and I just sort of verbally said that, is that R is always equal to one term divided by the term that comes before it, right? So for example, if I go T2 divided by T1, 15 divided by 3, that's 5. I could also go T3 divided by T2. 1875 divided by 15. That's also 5. I could go 1875 divided by 375. That would be T5 divided by T4. That's also 5. So that's one way, if you're trying to find the common ratio, that you can do so. Sometimes it won't be given to you. Okay, so what we're going to do now is try to figure out the general term for an geometric sequence, just like we did with an arithmetic sequence. Okay, so let's take the example of the first sequence that we looked at, which was the 3, 15, 75, etc. Okay, and we've got T1, T2, T3, T4, and T5. Okay, and the first term was 3, and then 15, and then 75, and then 375, and then 1875. And really what we want to do is try to express each of these terms in terms of the first term, T1 or A, and the common ratio, because that's really, those are the only two things that make one geometric sequence different from another one. Okay, so let's look at the first term. The first term is 3, that's just T1. The second term is 3 times 5. Okay. The third term is we take the second term and multiply that by 5 again. So this is 3 times 5 times 5. Okay. And then for the fourth term, we take the third term, multiply that by 5. So this is 3 times 5 times 5 times 5. And then similarly for the fifth term, we take the fourth term and multiply that by 5. So this one is 3 times 5 times 5 times 5 times 5. Okay, and what I can do now is group the 5s by multiplying, or by writing them rather in exponential form. Okay, so this one is just 3. This is 3 times 5 to the 1. This is 3 times 5 squared. This is 3 times 5 cubed. And this is 3 times 5 to the 4. Okay, and actually, if I wanted to sort of be consistent, I could actually write this as 3 times 5 to the 0, right? So that also has a times 5 to something. Because, you know, anything raised to the power 0 is just 1. Okay, and now what we can do is say, okay, well, how does the number of 5s compare to the term number? And we can see that it's always 1 less, right? The number of 5s that we multiply the first term by is always 1 less than the term number. So the general term, Tn, whoops, I didn't want to do that. Hold on. There we go. Tn is always going to be the first term times the common ratio 1 less number of times than the term number. Okay, or sometimes it's written this way. Where A is written instead of, or sorry, I messed up here. Not Tn, T1, there we go. T1 times R to the n minus 1, or instead of T1, we replace that with A times R to the n minus 1, and any of those are fine. Okay, so for example, if we want to find the general term for the 12th, find the general term and the 12th term of the sequence 3, 15, 75, 375, etc. So the general term would be Tn equals 3 times 5 to the n minus 1. That's the general term. And the 12th term is going to be 3 times 5 to the 12 minus 1, which is 3 times 5 to the 11. And I'm just going to do that on my calculator quickly. That is, wow, that's a big number. 146,000,000 484,375. Okay, so that would be the 12th term in that sequence. All right. Okay, let's look at some more examples. Okay, so suppose there were 3 bacteria originally present in a sample. Determine the general term that relates the number of bacteria to the doubling period of the bacteria. Okay, so if these bacteria double, then the T1 is how many bacteria there are originally. So T1 is the number of bacteria originally there, which is 3. And R, if they're doubling, is 2. Okay. So the general term of how many bacteria will there be would be Tn equals 3 times 2 to the n minus 1. Okay? All right. Let's look at another one. So suppose the smallest reduction a photocopier can make is 60% of the original. What is the shortest possible length after 8 reductions of a photograph that is originally 42 centimeters long? Okay. Well, T1 in this case is 42 centimeters, right? That's the original. And then each reduction is 60% of what it was. 60% as a decimal is 0.6. Okay. Now, the tricky part is this. 8 reductions, well, the 42 centimeters hasn't been reduced at all, right? So this is the original. Okay. T2 is the first reduction. T3 is the second reduction. So if we want to know what the 8th reduction is, we're actually not looking for T8, we're looking for T9. T9 would be the 8th reduction. Okay, so in general, Tn here is going to be T1, which is 42, times 0.6 to the n minus 1. Okay, so T9, which is the 8th reduction, would be 42 times 0.6 to the 9 minus 1 rather, which is 42 times 0.6 to the 8. And I'm just doing that on a calculator. And I get 0.705 centimeters. Okay, so that's how big it would be, the photograph would be, after 8 reductions. All right. Okay, so let's look at another example. This example is sort of a working backwards question. In a geometric sequence, the second term is 28. The fifth term is 1,792. List the first 3 terms of the sequence. Okay, so we know it's geometric. We know that T2, and T2, by the way, is T1 times R to the 2 minus 1. Okay, and that is that. We know that that's 28. Okay, so 28. Oh, sorry about that. Let's get back to where we were. Oh. Well, none of the notes. The notes disappeared on the second page. Okay. Well, let's start this example from the beginning in that case. Okay, so the second term is 28, okay, geometric sequence. So that means that T2 has to be T1 times r to the 2 minus 1. And that is 28. So 28 has to equal T1 times r to the 2 minus 1 is just r. Okay, we also know that T5 is T1 times r to the 5 minus 1. And so that is, what is that? 1,792 equals T1 to the power, times r to the power 4. Okay, so what we can do with these two, actually, is we can divide them. If we go 1792 divided by 28, that has to equal T1 times r to the 4 over T1 times r. And now we've eliminated one of the variables because T1 over T1 cancels. And 1792 divided by 28 is 64. And r to the 4 over r is r cubed. So therefore, r has to be the cube root of 64. The cube root of 64 is 4. Well, now that we have r, we can use either what we know about T2 or what we know about T5 to get T1. So I'm going to use T2 just because it's a little bit smaller. We know for T2, 28 equals T1 times r, and now we know that r is 4. So we can divide both sides by 4, and we get that T1 equals 7. Okay, so if we want to know the first three terms of the sequence, well, T1 is 7, T2 is 7 times 4, which is 28, and T3 is 7 times 4 squared, and that is 112. Okay. All right. So I'm not sure where those notes went, but my program quit unexpectedly. So anyway, that's okay. They made it to the video. Okay, so the next thing we're going to talk about is going to lead into something that you're going to look at next year. We're going to start to actually look at exponential functions. And that is, we're going to look at what would the R value be in these types of situations. And each of these types of situations has to deal with exponential growth. Okay, now the reason why we're talking about exponential growth with geometric series, or sequences rather, is remember we have that value R that keeps multiplying over and over and over again. That's repeated multiplication, right? Repeated multiplication happens to be exponential. Okay, so this is all what we're going to look at next is really going to tie into some of the content that you're going to look at next year in Math 30-1. And in fact, if you go into 30-2, you'll look at that stuff in that course as well. Okay, so what would the R values be for the following situation? So let's suppose a population grows at a rate of 3% per year. Okay, well, if a population grows at 3% per year, then the population the following year is actually going to be 103% of what it was before, because it's still going to maintain the 100% population what it was, and then it's going to gain an extra 3 people. So let's just say, for example, that you have a population of 100. Okay, the next year the population will still be those 100 people, but then you'll have an extra 3 people. So the population the following year will be 103% of the previous year. Okay, so what is the R value going to be? The R value is actually going to be this as a decimal. Okay. Now, if a population shrinks at a rate of 8% per year, we'll now take those same 100 people. The following year, there's 8 less people. So now, if your population was 100, the following year it's only 92. Okay, so the population the following year is 92% of the previous year. Okay, so what would the R value be? R is going to be 0.92. It's going to be the percent as a decimal. Okay, a house appreciates at a rate of 13% per year. Well, that means that it's gaining in value, right? So how much is it worth the following year? It's still worth what you paid for it, but then it's going to gain an extra 13%. Well, what you paid for it is the original 100%. So the following year, it's worth 113% of the previous year. Okay, well, that's going to correspond to an R value of 1.13. Okay, if a car depreciates at a rate of 23% per year, and usually with cars, that's what happens. Very rare for a car to appreciate, right? Depreciate means it's losing value. Well, then the following year, it's only going to be worth 77% of what it was. It's losing 23%. 100% minus 23% is 77%. So it's worth 77% of the previous year. Okay, so R equals 0.77. Okay, now how can we get these? Essentially, if something's growing, we take 1 and add the percent it's growing by. So this is 1 plus 0.3, right? C is also growing. This is 1 plus 0.13. Or sorry, this is 1 plus 0.03 was the first one, my bad. Okay, if something's shrinking, then we have to subtract the shrink rate. Okay, so for B and D, these were each 1 minus 0.08. This was 1 minus 0.23. Okay, and that's how we get these R values of, in the first case, 1.03, in the second case, 0.29, sorry, 0.92, in the third case, 1.13, and in the fourth case, 0.77. Okay? All right, so let's apply this to a problem. Okay? In 1990, the population of Canada was approximately 26.6 million people. Okay, so that's T1. And by the way, you guys, population growth, whether it be bacteria or people or rabbits or whatever, is almost always exponential, meaning that it can fit into a geometric sequence. Okay, and this is in 1990. Okay. Population for 2025 is approximately, or the projected population for 2025, because 2025 hasn't happened yet, is 38.4 million. Okay, so this is 2025. And we have to figure out what N is for 2025. And this was kind of tricky because if T1 is 1990, then 2025, you can't sort of go 2025 minus 1990 is 35 years and say it's T35, because you can only do that if this was actually T0, but it's not, it's T1, right? 1990 starts at T1, which means that this actually is T36 equals 38.4. Okay, it's almost like, if I don't know if you guys have ever done the problem with, this is a bit of a tangent, but I'm going to go there, with the fence post versus fence panel problem, right? So if you look at a fence, and you want to count sort of the length of the fence, let's say, right? Let's say these are each 1 meter, right? Well, then you'd count the number of panels. It would be 1, 2, 3, 4 panels, okay? But sometimes you have a situation where you actually need to count the fence posts. And the fence post is actually 1, 2, 3, 4, 5 fence posts. So the length of the fence is 4 meters, but the number of posts is actually 5 posts for a length of 4 meters. This is the exact same situation. The number of years is 35, but the number of quote unquote posts or terms is 36. Okay, so that's why the year 2025 is T36 and not T35. And this often happens when you're dealing with a geometric sequence with years. So you have to watch out for that. Okay. All right. So T1, by the way, is just T1, right? T1 doesn't have any R's in it, if you will. T36 though, which is 38.4 million, right? This is in million. This is also in million. T36 is T1, which is 26.6 times R to the n minus 1, which is 36 minus 1 is 35. Okay, so we can solve this actually a very similar way to the way that we solved the problem on the previous page, where we had two terms, but we didn't actually know what the common ratio was, right? And the way that we did that essentially was through division, right? So if we divide T36 divided by T1, then what we're going to get is 38.4 million. So I'm just going to write out the whole number over 26.6 million. So 26.6 million. And actually the zeros are going to cancel. That has to equal, this is what 38.4 million is equal to. So 26.6 times R to the 35 over, or actually, sorry, it wouldn't be 26.6. It would be, I'm writing everything in millions now, so I got to be consistent. Let me be consistent. 26 26,600,000 over, or sorry, times r to the 35, because that's what we said the 38.4 million was equal to, over 26,600,000. Okay, because that's what T1 is. Now, these 26,600,000 cancel. And so what we end up getting, and all of these zeros cancel as well, by the way, is that 384 over 266 is equal to r to the 35. Okay, now we can solve this by taking the 35th root, right, of this value, right? We can find the r value. Now, on your calculators, if you want to put in whatever square root you want, you have to hit the math button. Okay, so to get the root of 35, actually that's not true. You have to enter in on your calculator, enter in 35 first, and then hit the math button. And then hit number 5, where it says x root. And that allows you to put in whatever index you want. And then just in brackets, put in 384 divided by 266. And then go enter. Okay, so I'm going to do that right now. And what I get is, this is equal to 1.0105. Okay, now what does that tell us? That tells us that the annual growth rate is about 1.05%, because remember this 1.015 is 1 plus the growth rate. Okay, now, annual with 2 N's. What are we assuming here? Well, we're assuming that the growth rate is constant, right? And usually that's not actually the case. We were asked to talk about assumptions, right? So assumption, the rate is constant. Lots of things can happen that would interfere with that annual growth rate. One of them is immigration. Another one is economics. So for example, a lot of people are waiting a lot longer to have children or having less children because it's a lot more expensive these days to live. And so, you know, people can't support as many kids as they once were able to. And so people may not have as many children, and then our population might decrease, for example. So that would be one example of an assumption that we might make where the growth rate is constant and it might not be for population growth. Okay, so that is about it for geometric sequences. Tomorrow we're going to look at geometric series, and I will see you guys then.